Test. Is the mic on? Okay. I'm talking, I think. Okay, ladies and gentlemen, boys and girls, welcome to another Tech Day Live. Whoop, where am I? I'm here. For today, I hope to get 2 good hours out of this session. I'm gonna start with some machine learning. On my job, actually, I got an opportunity to change my position, and I'm gonna do more reverse engineering and some LLM actions. So I think I'm gonna dabble into this as well, even though I know that at least reverse engineering lies somewhere in the gray area, let's say. Doesn't matter. Let's start with some machine learning. Let's start specifically with decision trees. Decision trees. Okay. Bum, 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 bum. Okay. Can I? Why can't I write here? All right. Now I can. So let me change the color to something more colorful, so to say. Decision trees. Okay. So how I like to do these things is to kind of get the most basic explanation out of it, to at least build the foundation, and then I'm gonna do the textbook way. I'm gonna enter the textbook. I'm gonna see how decision trees are objectified there and defined there. So. Okay, decision trees. So, what is a decision tree? A decision tree is at least in ML, it's a flow chart like tree structure. I'm just gonna say tree structure. I think the other things that it's a flow chart like can be deducted on its own or learned later. So tree structure where each node, okay, so just a bit, no, what is my model here? Let's leave it at 200 maybe. Where each node asks questions such as, is there meat in this recipe? Apologies. Is there meat in this recipe? Is this age appropriate? Is this email a spam or not? And each branch is representing the outcome of the question. And the outcome of the question can be yes or no. And each leaf gives a final answer or prediction. For example, it's this spam or ham. Is this class A? In the case of the meal, example, I can say, well, has meat, doesn't have meat, and things like that. So it's a series of if-else rules that split data until you're confident enough to make a prediction. And there's a common joke that AI is just a bunch of if-else statements run together. You just need a strong enough computer in order to run it. And let me just show you this actually. Google.com decision tree diagram. Do I have it here somewhere? Yeah, decision tree, but I want it in. For ML, right? I'm on another. Just a second. Decision tree ML diagram. Okay. So there are some videos and stuff, but I want just an image to see. Maybe this is the best way to visualize this. No, I don't want all of this. I want just the image. Open image in new tab. Okay. So there's some other data. It's not a simple if-else statement. There is something called entropy, samples, value, class. I don't know if this is BMI. So we have BMI and glucose, which I assume are features. I don't know about the others. Are they related to the concept of decision trees or not? Let me just turn this off. Okay. So, as I said, the way I kind of like to learn things is by, I don't know, asking, for example, tchdy, just give me the simplest, most basic explanation of the topic, in this case, decision trees, and then we're gonna build upon that later on. Okay. I don't know, let's say one simple example is, let's say we want to, I don't want to do something stupid. Approve or reject loan applications. And we have a decision tree that might look like this. Give me another color. So let's say if my income is greater than, I don't know, let's say 50K, I have yes, I have no. So if my income is greater than 50K, what else? In America, they have something called a credit score. I picked up this example. I'm unaware of any of these concepts, but let's say credit. I have no idea what a good credit score is. Let's say, I don't know, 700. No idea. Okay, but if the credit score is greater than 700, again, you have yes, and then you have no, and here you can be approved, otherwise you're rejected, and you are also rejected if your income is not greater than 50K. So only in this case in which the income is greater than 50K and the credit score is greater than 700, we are approving this loan request. Otherwise, I don't know, tough luck, unfortunately. Too bad. But how it works behind the scene is we collect all the data. We have data and we have them labeled. Just a moment. Okay, so we have data and we have them labeled like, I don't know, let's say this is a snippet of a table. We're gonna have age, we're gonna have income, and then I don't know, some other data, 22, let's say 32K, 25, let's say 75. I have no idea. I'm just guessing number. So the tree, well, first of all, it's gonna pick up the best, not only feature, but also the best questions to split the data. It's gonna ask questions like, okay, which question splits the data into the purest groups? One of those questions is the one that we asked here, whether the income is greater than 50K. And this will then divide the data set into higher incomes and lower incomes. And we need to find the best split at each point. All right, we need to find the best split at each point. And yeah, like in other algorithms that we did, we are having ways of measuring how pure a split is. And in case of decision trees, we have concepts such, I don't know if this will be in the book, but let's mention it here. We have Gini impurity, and information gain. I hope this will be in the book. If not, I'm just gonna scrap it. But let's say gene impurity and information gain. Then we repeat the splitting. After asking for income, maybe we can ask for age, and then we just keep splitting basically until we have pure groups where we have all yes or no's, or there's a depth limit. Okay, so there's also the explanation about what makes decision trees great. I don't care about that. What I care about now is to do a bit of a more concrete example. So what do we have here? This is the code. I don't think I'm gonna jump into it straight away. So what do we have here? Actually, let's start with the code. The good old check, the good old default config, the save figure method. Okay, here we start training and visualizing a decision tree. Is this? Maybe I need to increase it a bit more. Okay. Training and visualizing a decision tree. So what is being done here? We load the data, we pull the petal length and petal width like we did in the last example. Okay, we have the labels, and then we just create a classifier. Okay, and we fit the data. This is like the basic way we use. We use machine learning algorithms, but Can we generate? Ah, we can also generate an image. Export graph with. So what is export graph with? This is some method, most probably. Okay, it's from scikit-learn. So I have my classifier. I have the file where I'm saving this. I'm having the feature names. I'm having the class names, rounded true, filled true. I don't know what these mean. I don't know what these mean. Then from, why is this not working? Have I run this? No module named graph with, so I need to most probably install this module here. What's the best way to do this? Should I just run the terminal? No, not start debugging. Run new terminal. Clear, and then I'm gonna run pip install graph with. That's it. Fast. Fast. Now if I run this cell. What the fuck happened? Why are you not working, brother? File not found error. Images path, iris tree dot. Where are my images? Iris tree dot. I don't see an iris tree dot file here. Iris tree dot. There's no file. So do I need to run this again? Why is this happening? Why is this happening? What's happening here? What is the error saying? File not found error. So make sure the graph with executables are on your system. Okay, it went deep into the sub processes here. Ah shit, I need to install it on my system. I don't want to install this shit on my system, man. But okay, let's move it here. Sudo apt install graph with. Will this work now? Oh, let's move this back here. I'm gonna remove it after the video ends. I need to add it into the notes. Remove graph with. What even is graph with? Graph with. Graphis is an open source graph visualization software. About look, last modify September 11. No, I'm sorry. I'm sorry. So what's the thing with this? That's it, right? It just generates. Okay. Hey, Captain, what's up, man? Oh, what's up, gal? GraphWiz also provides the dot command line tool to convert dot files to a variety of formats. So most probably the dot file is something GraphWiz specific. I'm sorry, I feel I don't want to install shit that I don't need on my laptop or my computer. I have a lot of things that I had to install because now I stream while I'm learning, and there's a lot of things that's just cluttering. And I think I'm gonna forget. I know. Hey, Antonio, what's up? I know about plot tree. I think for this case that they are specifically trying to visualize decision trees, I think, or something, right? I just have why did I install it? And I think I have tchdy or something. I hope I don't forget to remove it when I finish the stream. Maybe I can remove it now. Okay. GraphWiz also provides the dot command line tool to convert dot files to a variety of form. Okay. So it's something GraphWiz does on its own. Okay, making predictions. Wait, where's the book here? And what's the book saying about this? Okay, we use somewhere, yeah, source from file, and here it says we can use graphwiz.source from file, which is this method here to load and display the file in a Jupyter notebook. Okay. It also says here GraphWiz is an open source graph visualization. I mean, I don't want to shit on GraphWiz. It seems really nice. I just don't like things that I'm not using on my computer. And that are not beneficial or required to run everything else. Basically things that I'm never gonna use again. Okay. GraphWiz is an open source graph visualization software package. I know this. Okay, so this is our first decision tree, which is similar to the ones that I showed back then. So, all right, so you can select things. So it draws things, and you can most probably, I can copy this most probably, right? No, I can't. Device. Why do I allow? What? I can't right click on it. I can select it. Okay. So it checks, okay, if the petal length is less or equal than something. If it's true, so if it's true that the petal length is less or equal than 224, so it classifies it immediately. Otherwise, it checks the petal width. What's the guinea? Guinea is the what's the name of this? What's the name of this? Guinea or Gini is the Gini inequality metric, right? Yeah, no, Gini impurity metric. It will most probably come later in the book. But so this is like our first decision tree. True, false. Again, we have the petal width. So this is a metric. I hope we will find it later. Okay, these are the samples. I didn't know what the samples means, but the samples are the amount of data we are having and the amount of data we have in each leaf in the decision tree. Okay. So my question is, and I think this is a pretty good question. What the hell is this? It looks. It reminds me of Is my keyboard not working? But it is working. Okay, so it drew something. Let me think about what it drew. NumPy, we have plot, we have some colors. Well, I don't know what kind of a structure this is. It's just some kind of class, but we define 3 colors, which I assume are the colors of... No, it's the background colors. All right. Figure, what else do we have? Mesh grid. So I assume this is both vertical and horizontal coordinate system that they are creating from 0 to 7.2. Yeah, from 0 to 3. Okay. Okay, so it's creating a coordinate system. What the hell is Travel, man? What the fuck? I remember. I did one stream and I remember I came across Travel. I think it flattens the... Let me check. Lengths and widths. So if I print lengths, and then if I print length Ravel, what am I getting here? What the fuck, did it do anything? Blah blah. Ah, it's the last one. Yeah, okay. Basically Ravel or Ravel, I don't know how it's spelled or said. It just flattens the grid. Okay, flattens the grid, and NumPy C stacks them side by side. All right, so if I have something like this, I'm sorry, I'm just for me, in order to remember something, I need to do every stupid example in the book just to make sure I understand it. So I apologize, this is a bit too simplistic. What the fuck? I need to do Ravel, so it will... I need an NumPy array. Okay. Example NumPy array 1, 2, 3, 4, 5, 6. Print example Ravel. I mean, it would most probably be the simplest thing just to ask ChatGPT, but I realize as much as I keep asking him things, I keep remembering. Yeah, okay, wow. Example. What about example 2? Example 2, and here I'm gonna have, I don't know, 6, 7, 8. How's so NumPy C example Ravel example 2 Ravel. What am I having? Something is not right. And what is not right? Why is this not like, is the stupidest thing? All the input array dimension. Do they need to match their... Wait, 9, 10. No, it's still not working. What? Then I just wanted to see how this works. NumPy C. Okay, what I'm doing, I'm asking ChatGPT this. All right, it flattens a numpy array. I already know this. Wait, I okay, let me remove all of this here. So numpy, this method, this is it's not even a method. What the hell is this? It's a shortcut to concatenate arrays column-wise. Take multiple one-dimensional arrays and stack them side by side like columns in a spreadsheet. So if I have this, and then if I do combine, it's gonna be 1, 2, 3. Yeah, it's gonna be a two-dimensional array, right? No, it's not. What? So it stacks them side by side like columns in a spreadsheet. Man, numpy is a... Man, numpy is a black hole of knowledge. I always forget I should treat arrays, quote unquote arrays, in NumPy as matrices. Which I don't know why I forget, because I don't even know how matrices work. Sorry. Okay. So with the lengths and widths, I created a new structure. Which looks like this. Okay. So we converted it into the first element in the row is now the first element in a column. We basically inverse rows and columns here. Okay. Here, okay, here I'm using the decision tree to predict the class and every point in the grid. Okay, then there's some contouring and plotting done here. Oh, shit. What am I doing here? Zip, iris target names, yellow, circle, blue, square, green, triangle. So I'm enumerating. What the hell is zip? Ah, zip creates tuples out of this. So I'm gonna have three. What am I gonna have? 3 labels, and each label is bundled together with one of the colors. Then I'm plotting it. I'm plotting it only in case. Shit. What? What the hell is this? So I'm getting the first. Now I'm getting the first column, right? And I'm getting gold data, and then I'm checking whether the index that we currently are. What's y iris? That's why it's targets. Some just a second, sorry. So I'm learning against that. Then I have the label here. Iris, those are okay. All right. So for each of these targets, we plot them using a specific style and label. And then here, yeah, as I said, I'm getting column 0, which is this first column right here. And I select all rows. So this will be an array of all petal lengths, which is this first row. Why? I would most probably like create a new data structure in which this data will be an array instead of doing this. Hey, cool diaries. I'm just looking through these snippets for machine learning. Basically, I wanted to switch professions, and I don't know, I was really interested in machine learning, AI in general. It's the new cool thing. But a couple of days ago, my company basically told me, hey, maybe we want you to join our reverse engineering team. And I said, oh, why not? So I don't know if I I love machine learning, so for me this is really cool. But I also need to start doing. They told me I need to start doing reverse engineering, like on learning. I don't know if you guys know anything about this or where I can find some good resources on the topic of reverse engineering. I don't know, obfuscations and debugging Android APKs and stuff like that. I don't know anything about this. I need to learn. Maybe I could download an emulator and do something with it. But okay, well, let's go on. Okay, all rows, column 0, only the petal length. This guy here is an array of petal lengths. And this is a Boolean mask. Like we have in Photoshop, only black and white. And the Boolean mask says, okay, it's only true for the samples of this species. So if it's acetosa, so for example, if, I don't know what do I have. Okay, so if my index here is 1 and I have here y iris is, I don't know, 0 0 1 1 2 2, and if it's 1, I'm only gonna set, wait, I don't know, 0 0 1 1 2 2. Once I do this, is gonna be false, false, true, true, false. Fuck. False. So it depends on this. It masks the whole NumPy array. This is something I used. This is something I understood. Now this just draws the figure. I think it's a really nice figure. Not gonna lie. Okay, and you get this. Let me just make sure. So let's say I find a flower, an iris flower, and I want to classify it based on its petals. So I start here and then I check, okay, if the petal length is smaller than 245, and then I go left and right. Okay. Oh, nice. There's also some ad here. Amazing. I love it. I love it. No, I don't. Okay, Gini impurity. Oh, there's also a formula for it. Amazing, 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 amazing. Let's do this. So here it says, okay. Gini. Okay. I was wondering what Gini does. A nodes. Where are you? A nodes. Gini attribute measures the Gini impurity. A node is pure, in which case Gini is 0. This is pure. This is a completely pure node. So if Gini is 0, that means that all training instances belong to the same class. Okay. So we are completely sure that all the setosas are setosas. We don't have false positives, we don't have true negatives. All of them are where they're supposed to be. On the other hand, these two are okay. Seems like some of these are wrongly classified. So how does Gini impurity do? Where's my tablet? Where's my tablet? Where's my tablet? Oh, it's here. Okay. So Gini impurity. So there's actually a formula for it, which goes something like this. It's G. It's 1 minus the sum of, we start from 1, we go to the end of the samples, P. Now this is where I don't have idea what P does. So what's Gini impurity is, it tells us how mixed up the classes are in a node of a decision tree. A pure node, all samples are from the same class, it has a Gini of 0 like the orange one, all the other, or a very impure node have a high Gini score. So what do we have? We have for Setosa, what do I have for Setosa? All right. Okay. So in this case, in the where's the node that I wanted to do? This one. Let's do this one here, the green one. So what do I have? I have Setosas. I don't have any. So 0 out of 54. We have total of 54. Where's my mouse? We have total of 54 samples. So this is gonna be 0 P4 versicolor, but which one is this is the versicolor. So I have 49 of them divided by 54, and that is 0.907, and then I have a P of Virginica, and this is gonna be what, 5 out of 54, and this is gonna be 0.093, and these are big. I mean, all of them would sum up to 1. which makes sense because I'm dividing the amount of them over the total size of the samples. But this is not the end. Now I need to plug this into the Gini formula. And what's this? G, it's 1 minus, okay, 1 minus, this is what the sum here does. I need to sum all the class proportions. So 0.00 squared plus wait plus 0.907 squared plus 0.093 squared. Because of the minus here, all of these will be now minus as well. So what's the G? It's 1 minus O minus 0.822 minus 0.009. I'm just using the calculator. So it's around 0.169. Here it's 168. I think, I don't know, a decimal got lost here somewhere. So the Gini impurity is 0.169. It means that the node is mostly versicolor, but it's a bit polluted. It has some impurity due to some Virginica examples that are found there. And I basically could do another example. I can do a toy example just to drill this in. Let me change the color here. So let's say I have 6 elements in class A and I have 4 of them in class B. Let's say a node has 10 samples. Like this node here. It has 10 samples and 6 are in class A and 4 are in class B. So then I'm doing the proportions. P of A is 6 out of 10 is 0.6. By correlation, P of B will be 0.4. And then I do Gini, it's 1 minus, I'm doing the summation here, 0.6 squared plus 0.4 squared. This is going to be a minus now. Right? Hopefully 1 minus, so what do I have? 0.36 minus 0.16. Oh, I didn't know that you can do this as well. 0.16, so it's 0.48. I assume this means that this is, I don't know, somewhere in the middle. It's moderately impure. Actually, 50-50 is the most impure for a 2 class. So this is quite impure, it seems. Okay. All right. Simply explained. I like this. Well, thirsty. I should get some water, but let me just. Where did I stop? Okay, here it says decision trees are easy to interpret, which means that they are called white box models. Some other models are such as neural networks are called black box models. So they make great predictions. Nevertheless, it's hard to explain why the predictions were made. Okay, so for someone like me who likes shit explained, this would be very useful. For example, if a neural network says that there's someone particular in the picture, what has contributed to this prediction? We don't know. We don't know. Is it a certain facial characteristic like eyes or smile, or the way they dress, their shoes, skin color, I don't know, their environment? There's a lot of things, a lot of features that could be involved. Oh, there's even a field in machine learning which aims at creating systems, machine learning systems, that can explain their decisions in a way humans can understand. Oh, I heard that, for example, these LLMs, especially the big language models, you know, the big guys like Gemini and tchdy and fuck, what else? Grok. I don't know how Grok. I don't know where Grok stands in the pecking order, but I read somewhere that the developers are like completely unsure how it works, you know, under the hood, which is really interesting. All right, let's go back to coding, making predictions. Bam, this is done. You can access the tree structure via the tree attribute. Just a second, I'm sorry. 47, 52 minutes. I'm seeing, guys. I just need to. I'm just gonna say here. BRB. I just need to get, I don't know, a beverage, and I need to. I'm a bit stuck. I'm gonna stretch a bit, and I'm gonna be here fast, like 2-3 minutes stops. Thank you all. Okay, hello. Where did I stop? Estimating class probabilities. Okay, so what do I need to estimate? So, a decision tree. Continue writing this. Okay, you need the pink color. A decision tree can estimate the probability that an instance belongs to a particular class. Okay, so how does it do this? It traverses the tree to find the leaf node for this instance, and then it returns the ratio of training instances of class K in this node. Okay, so let's say we have a certain flower. Where's my drawing environment here? The petals are 5 centimeters and long and 1.5 centimeters wide. So what do I have here? I go back, I look at the image. So the length is greater than 2.5, so it goes here. The width is less than 1.5, so it goes here. So it should be the Virginica, right? 0% for iris setosa, okay. 90% for iris versicolor, but how? It's less than equal than 1.5. I'm an idiot. So it is versicolor. Or not? Let's wait. less or equal than. Yeah, so it's versicolor. Where's the code here? Oh, so this is the new flower with these custom petals. And then we predicted it's 1. Okay, these are just 2 different ways of showing the same data. What else? Regularization hyperparameters. What the fuck is this? Okay, before I continue, there's some, in the book at least, there's some. By the way, I'm following a book titled Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow. I don't want to, I mean, even if I want to show it, I think it would be illegal because I would get a copyright strike. So I'll try to paraphrase what it says here. So scikit-learn uses a certain algorithm called CART, C-A-R-T, or classification and regression tree algorithm to train decision trees. How the algorithm works is by, okay, it splits the training set into 2 subsets using a single feature, and we have a threshold. Okay, so let me just write this in. I don't need. Okay, CART, C-A-R-T, and it says stands for classification. I can't write all of this shit. And regression tree. So it selects, as it did in our example, it selected a feature and a threshold. How does it choose K and TK? Okay, so it searches for the pair K and TK, K being the feature, TK being the threshold. The pair produces the purest subsets weighted by their size. Okay, let's do some more math. Let's do some more math. Where the hell are you, Mr. Math? Okay, so it finds the best feature, it finds the best threshold, it puts the data into subsets, and then it repeats the process recursively on the subsets. So what does it do at each node? So there's a cost function which looks like this. KTK M left over MG left. No idea what any of this does. M right over MG right. All right, so M is obviously the total number of samples. M left and M right are number of samples in each branch. What's the G? G is the Gini impurity. Okay. So it's a recursive greedy process because it finds the best split now. And it stops when it reaches max depth. But it doesn't look ahead several steps, which means it's greedy. It means it might miss the perfect long-term split. But it's fast and effective. For example, okay. For example, let's say we have petal length, and let's say we have a class, and the class will only have b between 0 and 1. So if the petal length is 1, 2, 3, 4, not 4.5, 4 and 5, then I have 0, 0, 1, 1, 1. Okay. So cart does its own first split. It says, okay, let's split at t, or the threshold being 2.5. So in this case, we're gonna have left to be 1 and 2, and right to be 3 and 4. I don't know why I'm writing the decimals. So the classes are 0, 0 for the left group and 1, 1, 1 for the right group. And now I need to compute impurity of left and right nodes. Okay. As I already know, to compute impurity, I need to also compute the probabilities. G left is what? 1 minus 2 over 2 squared. It's gonna be 1 minus 1, it's gonna be 0, it's gonna be pure. Right is 1 minus 3 over 3 squared, same thing, it's gonna be pure. And then I'm using this formula to compute the weighted cost. Okay. Wait. So what do I have? I have 0, and I have my threshold is gonna be 2.5. So what do I have? M left over M, it's 2 over 5. I multiplied by G is 0, plus 3 over 5 multiplied by 0 is gonna be 0, which means this is the best possible split. But what if we tried, let's say, a worse one? What if I find that my threshold is 3.5? Okay, so then my left group would be 1, 2, and 3, and my right group would be 4 and 5. So on the left, I have 3 samples, and I need to check the purity. So if I want zeros, I have only 2 out of 3 zeros. That's my proportionality. On the right, I have what do I have? Wait. On the right, I have 1 and 1. So the Gini for 1 and 1 is going to be 0. Okay. But for the left, I have what? 1 minus. I have 2 out of 3, which are zeros, minus 1 out of 3, right? Which is a 1. It's gonna be 1 minus what? 4 nines. Minus 1 9 is gonna be 1 minus 4 9 minus 1 9. It's gonna be 0.444, which is worse than this. And then when we calculate the j as well, it's gonna be 3/5 multiplied by its Gini. It's gonna be 0.444 plus 2/5 multiplied by 0 is gonna be 0.266. Okay. So there's something else here. Let's run this. So there's something called make moons. So I assume that moons is okay. So moons is most probably a data set that we use freely from scikit-learn. Okay. So moons is creating a two-dimensional classification data set with a crescent moon shape. Okay, that's why it's called make moons. Okay, I think I get it now. So basically it's gonna create a shape that looks like this, and it's gonna fill it with data. I mean, we won't see the borders, we're only gonna see the data, and we can create probably another one like this. And they will most probably be intertwined. So most probably this is used to test how well are models handling non-linear boundaries. So the second thing is, here we create a data set of 150 points. They are shaped like two interlocking moons. Okay, as I said, they would. Okay, there's some randomness. And there is some reproducibility here as well. So what's the result? Here I have 150 elements, and each element has two features, X and Y, the positions. And on Y moons, I have only the labels here. Only the labels. Oh, before I continue, there is a wonderful discussion on G about, wait. Ooh. Genuine question. What would make you turn down $1 billion salary? So someone turned down $1 billion. Thanks for your $1 billion job offer, Mark Zuckerberg. I'm gonna pass. The loyalties and larger than life figures prompting some people to turn down insanely lucrative offers in the Silicon Valley right now. There's no way. There's no way someone is just being offered $1.1 billion, man. What? If they offer to pay you 1.5, they think you're worth more than 1.5. But 1.5 is already an amazing sum. Ah, it was actually 1.5 billion. The researcher who declined Zuckerberg's offer of $1.5 billion package over 6 years is thinking Machine's co-founder and ex-Meta staffer Andrew Tulloch. Man, take some balls. Take some balls to refuse that money, not gonna lie. Not gonna lie. My laziness, I would have to work for that money. Work ruins my company day. Ah, I know, man. I know. I don't want to incriminate myself, but I know. Oh man, I love fortune. Okay, let's continue. Let's continue. What have I done here? What else do we have here? Oh, there's another cool discussion. What's this? I'm too mentally drained for figuring out how to do stuff at my wage job. Work in a big tech company, so there's a lot of competition and people showing it. Yeah, man. Yeah. I can only imagine what happens in those even bigger tech companies. You lied. Coding is not so simple when you need to figure out stuff on your own. I plan to take in the Yeet route and become a tech lead manager soon. Okay. Everyone wants to be an engineer until they realize what? 85. Oh no. Oh no. Why are you making... Why is this bitch making this stupid face? 80% of all of your classmates are ugly. Fuck you, bitch. I got triggered right now. Alright, let's continue. So what do I have here? So I create two decision tree classifiers. The only difference here is that one has set it something called a regularization term, which forces each leaf to contain at least 5 training samples. Okay, why? Because it's gonna prevent the tree from becoming too bushy and overfitting small irregularities in the data. Okay. And then both of these trees are training the same data. Okay. Okay, then we have all of this. Why can't I select? Why is my control not working? Okay, for some reason my select all shortcut is not working on Visual Studio Code. Who knows? Who knows? Alright, what's the first thing? The function. Plot decision, no. Plot the decision boundary. So what's this function doing? It's a helpful function. Plot the decision boundary of a classifier. Alright. And the decision boundary is the margin between two classes. I learned this the last video from vector machines. Okay, so I have the feature matrix, I have the labels, the area to plot, and okay, these are just the numbers. Again, I'm creating a grid, XY, XY. Again, I'm labeling it. I'm predicting. Why is it using? Ah, okay, so it's using one of these classifiers. Okay, predict, reshape, contour, X1. So contour is gonna fill regions based on the predicted class, and it's gonna add outline lines, which are these lines right here, to show where the boundary cuts across. And what else do we have? Ah, okay, so these are the colors. These are the markers. We have a distinction between a circle and a triangle here. And then I'm looping over these two classes, only over the classes, and I'm plotting only the points belonging to each class. And for each one of them, I'm drawing I'm drawing a color, coloring them differently. And then this is how we plot this. Actually, we create subplots. So we have two of these. One of them is overfitting, is this guy. One of them is a bit smoother. Okay. So let me just see. Now, what I did now is I want to do this really complex. I think it's even a university book. So I'm gonna turn this off and I'm gonna open up a one that's a bit simpler. Okay. And now we are gonna go back to the concept of a linear regression. So just, I have here somewhere the points that I've been working on here. So this is all on linear regression. This is all data on linear regression. Ah, sorry, no, this is on linear SVCs. Where is, maybe here? Let's go back down. Let me turn this off and let me move this now to the middle. No. Okay. So where was I last time on the concept of okay, I'm just gonna go a bit way back. So let's look at another data set. I think I already have a data set here. Yes, I'm just gonna pick it up, copy it, and move it here. Okay. So this is a slightly more complicated data set of houses with their number of rooms. Oh, fuck. Guys, I need to end this stream. Apologies. I'm gonna be here tomorrow as well. And we're gonna do this.